Oh, I think I'm recording. Yep. Alrighty. Let me just double check. Sweet. So, hello everyone. This is Biochemistry 1 YouTube video, and today we're going to be going through electrolytes all the way down to buffer solutions. We're going to be covering some acids, some bases, and we're going to be doing some math. So, this section commonly trips some people up just with the math because if it's your first time doing it or you didn't have a huge chemistry background, it can be a little confusing. So I'll just do some background notes on electrolytes, acids, bases, some key terms that we need to know. And then I also made some math problems that we can go through so I can just walk you guys through, show you how to think through them, what equations to use, and then I'll let you guys go off on your own, practicing on your own. Um, Also, I was just thinking about this the other day, but if you don't go to the school that I'm making this YouTube video for, then I would probably find someone that's more educated on this kind of subject because I am tutoring towards a specific teacher and I'm not a biochemistry expert at all. I just do what I need to get by. So, with that out of the way, and hopefully no one is watching this from another school because I am not an expert, as I said. But let's get into it. So, I know we probably left off on electrolytes last time, and if you guys weren't at my tutoring session this past week, I'm just putting this out to make sure everyone's caught up to speed and is as prepared as they can be. So we'll start off with electrolytes, and electrolyte is just a solute that is a conductor when dispersed in aqueous solution. I just want to do some background terminology with strong electrolytes and weak electrolytes. So biggest thing we need to know with a strong electrolyte is that it completely disperses within an aqueous solution. And you can just see right here that we have NaCl plus H2O goes to H2O plus sodium and chlorine, I believe. But what I want you guys to focus on is right here, we just have a single arrow, which means nothing can go back to the original reactants. It completely dispersed into solution, and the main components are separated. So what we need to know is what falls under this category are strong acids and strong bases. They are both strong electrolytes because they completely disperse in a solution. But we'll move on to weak electrolytes, and they only partially disperse. And I know you guys are doing some ice tables and everything like that, so this is just a play on those original concepts. And we just need to know what falls under there are weak acids and weak bases. I'm not going to cover non-electrolytes for now since I mainly want to get into the meat of the subjects, but feel free to go back and read that on your own time. So we're going to start off with acids. What we need to know about acids are they are mainly proton donors. You will commonly see a hydrogen associated with an acid, and the more hydrogens they have signifies that they have a little bit more protons, and as a result of having more protons, they are just going to become more acidic, which means that they are going to be very low on the pH scale. And for those who are not familiar with the pH scale, I think it starts at 0, could start at 1 again. I'm not an expert on this, but we'll just call it 0 to 1 down here, and at the top, we'll go all the way up to 14, and usually neutral will be around 7. Anything greater than 7 right here is going to be considered more basic. I apologize for my handwriting. And then anything below 7, between the 1 to 7 range, is going to be considered acidic. So if you guys get a little bit confused with the pH scale and everything like that, I just recommend writing it down on your cheat sheet before the exam. And those help you keep your mind in order. So, what do we need to know about acids? And again, acids are proton donors. They taste sour, they are corrosive, and as you can see right here, commonly have a pH less than 7. So, if you look right here, this is just kind of demonstrating how an acid can form a conjugate base. We said that the acid right here, HA, when it goes through a reaction, gives away a proton, and also you're left with a conjugate base right here. And when we cover bases, it's basically the exact opposite. That conjugate base right there will gain a proton, and then it'll turn back into an acid. So I always write, when I get confused, these little HA goes to H plus A, and it helps me kind of keep my mind right. So We have two categories of acids that we're going to be talking about, strong acids and weak acids. Again, similar to electrolytes, strong acids completely dissociate in a solution. On the pH scale, they're going to be right in here between 1 and 3, which means they are highly acidic. And then, as you can see right here, similar to the strong electrolytes, we just have a singular arrow going towards the products from the reactants, signifying that the acid completely dissociated in the solution. And then we have a little list of strong acids right here. Historically speaking, you guys will hear me say historically speaking, I have not seen too many questions pertaining to strong acids, maybe one here or there, but I would highly recommend just memorizing these lists of strong acids, because you never know what Dr. G is going to throw at you, and it's better to be over prepared than under. So go down and memorize these, come up with a fun acronym or something, and keep on going. Now we come down here to weak acids. And again, similar to electrolytes, they don't dissociate completely. They have a low pH, but they're higher than strong acid. They're going to be in the 4 to 7 range, so more on the upper scale of the acidic side right up here. And what we can see right here is we have a double-sided arrow, which means it doesn't dissociate completely. We still have presence of reactants, and we also have presence of products in the same solution. And furthermore, they have a lower conductivity compared to strong acids. So that's kind of the backgrounds on acids. Now we'll move into bases. Bases, as you can see, are proton acceptors, and also make sure you can recognize the terms as a proton donor is associated with acid and a proton acceptor is associated with a base, because in the questions that you will see, he does change the terminology a ton when referring to acids and bases, and it's always good to have an understanding of what is a proton acceptor, what is a proton donor, and that'll just kind of help you reason through some problems. As long as you guys get the concepts and understand the concepts, you guys should be able to answer any kind of question that's thrown at you. So, bases, you'll commonly see them just written as, for this example, a singular A. We do not have a proton. We do not have an acidic element. We are an overall basic form. And as you can see right here, a base plus a proton will turn into a conjugate acid. And I always just like to say, anytime you see a proton specifically to this section of material, just kind of assume it's going to be a little bit more acidic. What we need to know about bases is they taste bitter. They have a pH greater than 7. So if we do this little pH scale again, right here with 7, 14, 0 to 1, we are going to be referencing everything above 7 right in here for a basic component. Bases are corrosive, and then again, similar to electrolytes, we have strong bases and weak bases. So strong bases are going to have a high pH between 10 to 14. We can see right here in this little equation, we have a singular arrow again, meaning that the reactants dissociate completely. And then we also have weak bases as well, and very similar to acids and electrolytes, has the double arrow, which means we still have presence of reactants and products in our solution and did not dissociate completely. The weak bases, again, will have a high pH, but they will be lower than strong bases, between 7 to 10. So I'll put that right there for weak bases, and I'll put this little orange one up here for stronger bases. And again, they have lower conductivity. And then I've been referencing the pH scale. These two equations right here are very good to memorize, because in a lot of the questions you guys are going to be seeing, especially pertaining to weak acids, Dr. G is going to have you give you some variables. He's going to give you some numbers, and he's going to be like, hey, here's a 0.2 molar concentrate or 0.2 molar concentration of a weak acid, and it has a Ka of blah, blah, blah. Find the pH for it. And don't worry, I will walk you guys through after we get through this background knowledge. But these two equations, when you're practicing problems, make sure to write them down, kind of have a little cheat sheet for yourself when doing the practice problems. But if you do it enough times, these equations will become ingrained in your brain, and it will be so much easier to go through problems. So the more reps you do, the better you guys will be at this. And I will skip through some material on here just so I can keep the video in a reasonable time. So you're also going to have variables of H plus and OH. H plus meaning acidic contents, and OH meaning basic contents. Normal blood pH is about 7.4, and the higher the pH, the lower the hydrogen content, which makes sense because protons, aka hydrogens, they are an acidic content, so the less you have of them, the higher the pH is going to be because it's going to be more basic. Yeah, just feel free to read through here. Again, this is more of an overview than anything to get you guys on the right path. In the tutoring sessions, I do go a little bit more in depth with a lot of this stuff, but for now, it's just going to be a lot more basic overview. So now we'll be talking about Ka. You guys heard me just mention a second ago. So Ka determines the strength of an acid or base. And what I want you guys to know is the larger the Ka, the stronger the acid. So I did skip by this in the acid component. So if we're to talk about this real quick, we have strong acids, and then we have weak acids. So we know for at least weak acids for now, the larger the Ka or the greater the Ka equals the stronger the acid, which means it's also going to be lower on the pH scale. So these arrows might be a little bit confusing. So, oh, I didn't know I could do that. How do I get that back? Oh, well, oh, hey, there we go. So the higher the Ka, the stronger the acid, the lower on the pH scale it's going to be. And this pertains mainly to weak acids because when we get to strong acids, that Ka is going to be so large that it's almost pointless to use it. So when people are referring to strong acids, the common term you're going to see is pKa. And that's basically the inverse of a Ka. You put Ka through a negative log, and that will find you your pKa. And what I always like to say for pKa's, it is very similar to pH. So let's say you have an acid and it has a pKa of 2.3, and you fill a jar up just with that strong acid. The pH of that jar is going to be around 2.3 because it is mainly filled with a strong acid. And just locking your guys' mind, anytime you see pKa, know it closely resembles the pH of that solution as well. So just to recap, for weak acids, we're going to be looking for the Ka, and the higher the Ka, the stronger the acid, which means it's going to be lower on the pH scale. Now, when we look at strong acids, we're going to be seeing a pKa, and that is highly resembles the pH of a solution. So if we have a pKa of a strong acid around 2.3, that means the pH is going to be around 2.3, signifying that it is a stronger acid and it is pretty low on the pH scale. And if we remember just previously, our pH range for strong acids is going to be about 1 to 3, and our weak acid pH scale is going to range between about 4 to 7. Now with that out of the way, we'll keep on moving down, and this equation right here, we will use this specifically for weak acids, and I will go over it in a second when we do some of the practice problems. But here's some practice problems within this study sheet. You guys can do them on your own time, gives great breakdowns of how to do these problems, and also just kind of helps you see what you need to do, how you need to do it. But the last thing we're going to talk about real quick are buffers. So buffers are made up of a weak acid and a conjugate base, the weak acid being the proton donor and the base being the proton acceptor. These are terms we just covered, so you can see they come back a decent bit. Buffers are designed to resist pH change in a solution. So when a buffer is in a solution, if let's say you have a pretty acidic solution, you have a buffer in there, and you start adding some base to it to make the overall solution pretty basic, you will, actually, I'll just draw this chart right now. So, let's say we have a pH scale right here, and down here, OH is going to resemble our base. Let's say we have a solution with some acid. We are going to be adding that base to the acidic solution. So down here, pretty low on the pH scale, we have a pretty acidic solution. We start adding some base, and as you can see, it starts rising on the pH axis, which means that our solution is becoming a little bit more basic, but then it's going to flatten out for a little bit. And then once we reach a point, it's going to start shooting back up and becoming more basic. But this flat line right here represents a buffer in work because you are consistently adding base to the solution, but that buffer is trying its hardest to resist a pH change. So within that specific range, you can add a decent amount of base and it's not going to have a huge effect on the pH of the solution until you reach the breaking point of that buffer. And once you add enough base to overpower that buffer, of course, it's going to start rising in pH because it's becoming more basic with the more base you add. But the overall concept for buffers is resistance to pH change, and it's usually going to flatline when you look at a pH versus base chart right there. Good buffers have a pKa approximately equal to the desired pH. So let's say we have a solution. Let's say we have a solution with a pH of, let's just go 7.2. Keep it neutral. And we want to add a buffer to resist pH change for that solution. And let's say we have a couple options. I'll make a little buffer list right here. We have a buffer that has a pKa around 3.2, a pKa around, let's go 7.4, and a pKa around, I don't know, let's go 9.1. So we have a list of 3 different buffers that we can use to add to the solution with a pH of 7.2, and we're trying to find the best buffer that will operate at its highest efficiency within a solution. We're not going to put a buffer with a pKa of 3.2 in that solution because, again, pKa is very similar to pH when referring to acids. So if we throw a buffer of 3.2 in there, the pH is already way too basic and way too high for that buffer to operate efficiently. And then let's say we want to do a pKa of 9.1. Well, that buffer has a higher pH, representing that is a lot more basic. And again, look at how much of a difference there is between 9.1 and 7.2. We have to add a decent more base to that solution to hike up that pH so it will operate efficiently towards the buffer, because we have to get that pH up around 9.1 for that buffer to start kicking in and operating pretty well. So the best choice of buffers to add to the solution would be a pKa or a buffer around 7.4, because it is only 0.2 off from the actual pH of the solution. So when we throw that buffer in there and we start adding more and more base, that buffer is going to start operating, because as soon as it hits around 7.4, that buffer is going to start kicking in and act a lot more efficiently compared to a buffer of 3.2 or 9.1. So that's just kind of a background. And again, if you guys are confused or just want me to go a little bit more in detail, please shoot me a text. I'm always happy to answer questions because I really want you guys to understand this and knock these quizzes and exams out of the park. And here's another little equation that we got to know. This is the Henderson-Hasselbalch equation, and this specifically pertains to buffers. And again, I'm going to go into a little bit more detail with it in a second. But whenever you see a problem that refers to a buffer or has even the term buffer in the question, I want you guys to think of this equation right away. We'll talk about intracellular buffers right here real quick. We'll just throw this in. It's a good concept to know, and it's kind of playing on just that little example I gave with the pKs and the buffer right here. It's basically the exact same concept. So intracellular buffers, they are pertaining to something inside the cell. And for this specific example, and the examples you will probably see on intracellular buffers are going to be pertaining to phosphoric acid. And what I want you guys to see is this phosphoric acid has 3 hydrogens with it in its initial phase. And what did we say about protons and hydrogens earlier? The more you have, the more acidic you're going to be. So phosphoric acid does have the ability to donate 3 protons because it has those 3 protons in the starting form. And if you guys look over here, we have pKs for each different phase of the phosphoric acid. So in our starting phase right here with H3PO4, if we start dissociating that and it tosses off just 1 proton, the pKa for our solution is going to be around 2.1 because we still have 2 protons with phosphoric acid. So that is also going to keep our pKa low because, again, pKa is highly resemblant of pH. So if we still have 2 protons, it still has a decently acidic component to it, and that's going to keep our pKa low because it's going to be resembling a similar pH. Now, if we take that H2PO4, when we bring it over here and we're like, all right, let's dissociate again. Let's get rid of another proton. As you guys can see, we go through this partial dissociation. We have another proton thrown off, and look, we only have 1 proton associated with phosphoric acid now. And if you guys look over to the associated pKa, we can see that the pKa now is around 7.2. This signifies that we lost another proton, but we don't have as many protons with this HPO4 as we did compared to H2PO4 or the original H2PO4. So since we have less protons and less of an acidic component, our pKa is going to rise because the whole solution is, or the component, the phosphoric acid, however you want to look at it, is overall just becoming more and more basic. And that explains the higher pKa, because as we get more basic again, we're going to be going up on the pH scale, and we are going to be rising more towards a more basic component. And then if you look at this last one, we're like, oh, we have one proton left, let's get rid of it. We put it through a reaction, lose that last proton, and now look, we're only left with PO4 3 negative, or however you want to say it. I'm not great with words, so make fun of me in person, don't laugh behind my back. Actually, I was trying to make a joke there, and I just lost my train of thought, so I apologize for that one. But as we can see, we have no protons left here, which means we really don't have an acidic component left with that PO4, and as a result, our pKa is going to rise up to 13.2, representing that again, we are becoming more basic because we lost our acidic components. And then right here, with this little example right here, they're like, if you want a pH to be 7.4, and I guess you're throwing in intracellular buffers, and you want a desired pH around 7.4, it's a lot easier to get to 7.4 using a pKa around 7.2 already, because this little component right here is basically representing how much base we have in a solution and how much acid we have in a solution together. And we can modify both of these variables to change the overall pH of our solution, but this 7.2 right here is representing our starting pH for this buffer. So our starting pH for this buffer is at 7.2. And over here we have this log component. So what this log component is demonstrating is how much base are we going to add, or how much acid are we going to add to change, or to add to change this pKa right here to get to a desired pH of 7.4. So kind of going on the previous components that we talked about right there, if we use this top equation right here and make a buffer out of it and try to get to 7.4, our starting pKa is going to be at 2.1. So instead of 7.2 right here, our starting pKa would be at 2.1, and we would have to add so much base to the solution to get to hike all the way up to a pH of 7.4. And then if we use this bottom equation right here, and it's like, all right, well, let's try this. Let's do a pKa of 13.2 and then add a ton of acid to it to drop the pH. It's just going to be a pain in the butt to get all the way back down to a pH of 7.4. So by using this middle equation with a pKa of 7.2, we don't have to add too much base to the solution to get that overall pH to rise, because we're only 0.2 off. We have to add less base to the solution to get the pH to rise, and overall it'll just be a lot more efficient to have a starting pH or pK around 7.2 and to influence that instead. Whew, all right, that was a mouthful. We covered very quickly a decent bit of information. So again, any questions, shoot me a text. I'm always happy to answer. But for now, we are going to get into the math component, and I'm going to show you guys. I'm going to give you a background quickly on the equations when I go over to the other sheet, and then we'll go through some practice problems. So let me get out of here. Let me jump in here. So as you can see, I got some practice problems down here, but we'll get to that in a second. So the common questions you guys are going to see pertain to either weak acids or buffers. And each problem set has a couple different equations we use, a couple different conversions that we need to make. And I'm going to walk through them right here to give us some packing, and then we'll go into the practice problems. So anytime you see a weak acid mentioned in a problem, the first equation I want you guys to think of is hydrogen concentration. So this equation is trying to calculate how many protons, or what's the concentration of protons that we have in a solution. So to find that, we are gonna square root HA times Ka. And if you guys remember Ka is highly representative of a weak acid. And if we remember, the higher the Ka, the stronger the weak acid. And what I also want you guys to know is this HA variable right here is just signifying the molar concentration of an acid that we have in a solution. So if you guys see a practice problem, and I'll just use the same example that we're going to go through, if you guys see a 0.2 molar concentration of a weak acid, that 0.2 is going to go right in that HA slot right there. And let's say it has a Ka of 6.2 times 10 to the negative fifth or something like that, that Ka is going to go right in that Ka slot. And then what he might do is Dr. G might try to trick you up. He might really try and test your knowledge. But good thing we're going over this now because I'm going to try and get you guys as prepared as I can. So what he might do is instead of a Ka, oh, I didn't realize I was deleting that. Instead of a Ka, he might give you a pKa. And you're like, whoa, that doesn't go with a weak acid. You only see those with strong acids. I know, but we need to know how to convert back and forth. So to find a Ka from a pKa, the equation we're going to use, wait a second, I got all backwards on myself. Oh my goodness, I just had a brain fart for a second. I apologize. So, rewind everything, ignore what I just said for a second. Basically, what we're going to do is I'm going to show you how to find a pKa from a Ka, and I'm going to show you how to find a Ka from a pKa. So let's say you want to find a pKa from a Ka. The equation we're going to use is negative log Ka. We're going to negative log the Ka, and that is going to help us find our pKa. And again, we are going to have a large numeral value in this Ka slot, and when we negative log it, it's going to give us a very manageable number over here, maybe like 3.4. And if you guys remember, pKa is highly resemblant of pH. So if you have a high Ka and you negative log it and you get a pK of 3.4, you can assume the general pH of that acid, that weak acid or whatever you're using is around 3.4. Now, let's say, well, Ryan, you just showed us how to get a Ka to a pK. Well, how do we get a pK to a Ka? Well, I'll show you. So let's say we want to find Ka. What we're going to do is raise the pK to the negative power of 10 or whatever, so, or 10 to the negative power. So let's say we have a pK of 3.2. And we're like, okay, well, let's find the Ka of that. All right, all we have to do is take 10, raise it to the negative power of 3.2. We just raise the pKa up on top of the 10, and we just put a negative in front of it, similar to how we have a negative log right here. We're just raising it to the negative, or a negative power. Oh my goodness, I am all over the place in my words today. We're just raising it up above the 10 and putting a negative in front of it, and that is how you go back and forth between Ka and pKa. So basically, if you guys want to do a quick order of processes on what I do, let's say he gives us the molarity, which again is going to go in that HA slot, and then let's say he gives us the Ka. Ka, which is just going to go right in the Ka slot. Basically, all you do is you plug that in, you plug that in right there, and what I like to do is multiply those together before I square root it, and then you will have a value under there, you square root the value, and it'll give you your hydrogen concentration. So from here, let's say you found your hydrogen concentration, and he's like, okay, well, I want you to find the pH now. Well, it's super simple. All we're going to do to find pH from a hydrogen concentration is, again, we're just going to negative log it. We're going to negative log our proton concentration, and that's going to give us our pH. So for a weak acid, he can give you all these variables, and look, you guys can find the pH pretty simply. Now, what he also might do is he might reverse it on it. He might say, well, here's the pH, and maybe here's the molar concentration, but I want you guys to find the Ka, and you're like, oh crap, like this is out of order. What are we going to do? Well, I'll tell you what to do. What we're going to do is, let's say we just have a starting pH here, and we need to go all the way back down here, and I don't know, I'll probably have like a couple weird steps in here. But let's say we want to find the Ka. So what we do is we take this pH, and to get back to our normal equation up here to find our Ka, we need to get this pH back to our hydrogen concentration. And very similar to going back and forth with the pK and Ka, what we're going to do is we're going to take our pH and again just raise it to the negative power of 10 to find our hydrogen concentration. 10 to the negative pH. Boom. And from here, we'll have our hydrogen concentration found. And what we do is we just plug it back in to this equation down here. And so now, let's just say we have a molarity around 0.2, just for an example. What we're going to do is we're going to plug 0.2 in right here, and we have our missing variable of Ka right here. So now we need to isolate Ka to find that variable. What we're going to do to get rid of this square root is we're just going to raise it to the power of 2 on both sides. And what I commonly like to do too is, if we're raising to the power of 2 If anything's under a log, you can isolate the variables separately. So what I like to do is do that, 0.2 times da 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 of Ka raised to the second power. And what that second power is going to do is it is going to get rid of that square root right there. So our end equation will kind of look like this. 0.2 times Ka, and then what we'll do is just divide, and then our variable over here will be equal to Ka. Yeah, that was a lot of talking for theoretical problems, and we'll get to those in a second, but secondly, what I want you guys to look at is how to go through buffer equations. So kind of going back to what I said with that original packet, with our buffer solutions, it is pH is equal to pKa plus the log of a base over an acid. This section right here is talking about what we are changing in the solution, the concentrations of bases and acids. This pK right here is representing kind of very similar to the original pH of the buffer and how this component is acting on the pKa to change the overall pH of the solution. So a couple different things you're going to see in here. You're going to see a lot of variables. You are going to see molar concentrations, you're going to see millimoles, and you might even see grams. So basically what I like to do is anytime that you see a molar concentration or millimoles, I personally like doing everything in millimoles, but these units pertain to the base and acid section of this equation. And anytime you do any division between the base and the acid up here, they need to be the same variables. So if you have an acid in millimoles and you have a base in a molar concentration, you need to make sure those variables are the same either by converting the molar concentration to millimoles or the millimole amount into a molarity for both the base and the acid, so you're working with the same variables. Now, you're like, well, Ryan, how do I convert these variables back and forth? Well, I'll tell you. Right here, this big M is going to stand for our molar concentration of a solution. And basically, a molar concentration is how many millimoles do we have in a solution. Oh, again, messing up my words. I apologize. It's getting to the afternoon. I haven't taken a nap. I'm starting to slow down a little bit. But basically what it's talking about is how many millimoles of a specific substance do we have. So let's say we have 18 millimoles of an acid. And let's say our overall quantity for our solution is, let's just go 200 milliliters. Basically what we do is we just divide 18 millimoles divided by 200 milliliters, and that gets us our molar solution, which would be 0.09. Now, that is how you get from millimoles and milliliters to a molar concentration. And let's say you want to follow my footsteps and do everything in millimoles. So let's say we don't know how many millimoles we have. Let's say instead we have a 0.2 molar concentration of an acid, and we don't know how many millimoles, but we know we have a 200 milliliter solution. So let's find some millimoles. All we do is times 200 on this side times 200 on this side, and boom, we have 200 times 0.2, and that equals 40 total millimoles of acid in a solution. So you guys will see how these concepts come into play, but I'm just giving you guys some background on how to do some of these conversions pertaining to the problems. You can see what I mean in about now. So we're going to be jumping in some practice problems here, and if you guys want, feel free to pause the video, try and do these yourself. If you think you found the right answer, great, keep on cracking at it. And then I will just walk through the problem just in case anyone gets confused. But right now, what we're going to start off with is a weak acid problem. And if we remember, our main equation we're going to be using for weak acid is hydrogen is equal to the square root of HA times Ka. And as you guys can see right here, that little scenario I talked to you guys about with a pKa, we're like, oh crap, he gave us a pKa instead of a Ka. So let's figure it out. So to begin anything, what we want to do is convert that pK into a Ka to fit our equation. So what we're going to do is we are going to find our Ka, which is equal to 10 to the negative 5.3 because we want to raise that pKa to the negative power of 10. So our Ka is going to equal 10 to the negative 5.3 is going to equal about 5.011 e to the negative 6. So now we have our Ka, so now we can kind of proceed with the question. So we also see that we have a 0.2 molar concentration, so that fills that HA variable right there. So let's plug some of these variables in. HA, or hydrogen concentration, is equal to 0.2 times 5.011 e to the negative 6. And as I said from right here, I just like to multiply my variables together before I square root them just to keep everything neat. Times, well, let me put this in parentheses real quick. I don't want to mix anything up. 0.2 times da-da-da. And what that's going to do is that is going to give us a value of 1.0023 e to the negative 6. So sweet, now we can square root it. Perfect. So now we square root that value, and that will give us a hydrogen concentration equal to 0.00010011865. So now we have our hydrogen concentration, so let's find the pH. And if you guys remember from earlier, the equation that we are going to use to find our pH is going to be pH is equal to the negative log of 0.00100111865, because that is our hydrogen concentration. Again, I'll just write the equation right here. pH is equal to the negative log of our proton or hydrogen concentration. And so now all we do is negative log this value. And drum roll please, that gets us a value or a pH of 2.99. So the answer in this case would be B, 3.0. We just found the pH for this problem. Now that we have the pH, let's go in the reverse order just for fun. So we have a pH of 2.99. And let's say we just keep that molar concentration of 0.2. So let's find the Ka and then even the pKa just to get comfortable with going back and forth. What we are going to do is erase all this first. Oh. Sweet. Just erased all that. So let's say we have a starting pH as equal to 2.99, and we want to find our Ka and our pKa. Again, we have it up here already, but just for the sake of it, we're going to run through it again. Just act like you don't know it. So to begin with, we need to find our hydrogen concentration, because again, I should just keep a list of the equations right here. We want to find our Ka over here, but we need a hydrogen to even begin that equation. So to find that, all we're going to do is raise our pH to the negative power of 10. So 2.99, there we go. So hydrogen concentration, finding it from pH, 10 to the negative pH up here. And then that gives us a value, 10 raised to negative 2.99. That gives us a value around 0.001023293, going da-da-da-da-da. So now let's plug it into our main equation. So we have hydrogen concentration of 0.001 is equal to the square root of HA times Ka. So we can kind of isolate those variables here. What we're going to do is, again, what I like to do is isolate the values and raise to the power of 2 for each one to get rid of that square root. So what we're going to be left with is 0.001 is equal to HA times Ka. And then I'm just going to erase all this previous work up here. I'm going to shift this guy up here. Sweet. So we have this equation sitting at us right here. So if we square our hydrogen concentration, we're going to get a value of 1.047 e to the negative 6. is equal to, and this HA valuable again is just going to be filled in with that 0.2 molar concentration right there times Ka. So what we're going to do is we're going to divide 0.2 and divide 0.2 over here as well. And that is going to give us a value of 5.23 times 10 to the negative 6. That is equal to our Ka. So hey, we found the Ka. Well, what about pK? Well, to find the pK from Ka, all we're going to do is negative log it. Is equal to negative log of Ka. Look at that. So negative log of our Ka is going to give us a pKa of 5.28. And look at that. Right back to where we started. So I just took you guys forward and backwards through a weak acid problem. Hopefully that made sense. Again, pause it, go back, rewind it, do it as many times as you need to understand what I just did. I tried to lay my work out as clearly as I could, but you know, do your best. Again, shoot me with any text or questions. I'm always happy to answer. So, got a little parched. What we're going to be doing now are buffer problems. And what you guys will commonly see is the term buffer will be in the problem. So we got buffer down there, and we also have another buffer problem down here. This is a pretty easy buffer problem right here, and this is a little bit more complicated buffer problem right here. I just wanted to throw both on just so we'd be comfortable doing whatever we need to. So let's look at this question. Estimate the pH of a buffer made from benzoic acid with a K, blah, blah, blah. Let me restart. Estimate the pH of a buffer made from benzoic acid. The benzoic acid Ka is equal to 6.2 times 10 to the negative 5th. And then it's asking us if the concentration of the proton donor in the system is 0.2 molar and the concentration of the proton acceptor is 0.5 molar, let's find the pH of this buffer. So going back to kind of the theoretical part that we talked about, our proton donor in the system is going to be our acid because it has a hydrogen and it wants to give it away. It wants to donate a proton. And then our proton acceptor is going to be a base because it wants to accept those protons. Yes, sorry, it is going to accept those protons and it's going to become more acidic if it accepts those protons. But these two terms are just need to know terms. And again, he is going to change the wording of these questions all over the place. He's going to have acids listed, a different thing. He might give you the actual name of the acid, the actual name of the base. But for this question, we're going to use proton donor and proton acceptor. So estimate the pH of a buffer made from benzoic acid. All right, we can do that. So our main equation is going to be pH is equal to pKa plus the log of base over acid. And the first thing I hope you guys saw is, hey, he gave us a Ka, but we need a pKa for this. So we get to do another fun conversion. What we get to do is negative log the Ka to get our pKa. So what we're going to do is we're going to negative log the Ka, so negative log 6.2 times 10 to the negative 5th, and that is going to give us our pKa, which will be negative log 6.2, negative 5, boom! Our pKa is going to be around 4.2. So we know our pKa now is around 4.2. So we have another variable for the equation. Also, rewind a little bit. What I like to do here too is I like to write my variables on the side of the page and have all my variables in order before I even do this question. So we know that we need to know a concentration of a base. We need to know we know we need the concentration of an acid. We know we need a pKa. And for this one, there's not as many variables, so there's not huge of a list. So we know with the proton acceptor, oh, that's messy. With the proton acceptor right here, we know that we have a molar concentration of the base. So our molar concentration is 0.5 molar. And since both the acid and the base are in the same variables as a molarity, I don't need to do any changes. I don't need to convert to millimoles. They are both in the same variable, so we can use them in the problem. So proton acceptor, which is going to be our base, our concentration is going to be 0.5 molar. And then if we go to our proton donor in the system, which is going to be our acid, we can see that we have a 0.2 molar concentration. So look, right there, we already have our value for our base and our value for our acid. And we just calculated our pKa, so we know we have a pKa of around 4.2 for this buffer. So let's plug some of these variables in. pH is equal to 4.2 plus the log of base over acid, so 0.5 molar over 0.2 molar. Would you look at that? So now we'll just do some calculations. And again, what I really want you guys to hammer on is memorizing that's always base over acid, base over acid, base over acid, base over acid. I will say it 10,000 times until you guys get it, because it is just such a big concept and so many mistakes can happen from flipping the acid and putting the acid on top and the base on the bottom. So besides that tangent, let's get back into it. So pH is equal to 4.2 plus the log of 0.5 molar over 0.2 molar. And again, going to say it again, our base over our acid. So let's calculate this logarithm real quick. Log of 0.5 divided by 0.2. That will get us pH is equal to 4.2 plus, that'll get us a value of 0.3979. You guys don't have to carry the variables out as far, but I'm just going to write them out. So now we know our logarithm is complete and we have a value of 0.3979. And basically, again, what this question is referencing, how much of the base and acid concentration affects our pKa and overall changes the pH of the solution. So when we add these together, 4.2, which is our pKa, plus 0.3979, which was our logarithm of the concentration of base and acid in our solution, we can see that our pH changed from this pKa to 4.5979. And if we round up, our pH is actually 4.6. But we can see that this concentration of acid and base brought our overall pH from 4.2 up to 4.6, so plus 0.4, and that's how much of an influence the base and acid concentration had on our pKa, and that's how much the pH changed by for it. And I hope you guys are picking up what I'm putting down. I might be explaining this in kind of the wrong terminology, so again, if you don't go here and you're like, oh, this guy's not saying this stuff right, well, I'm sorry, I'm not an expert, I just like math. So that is how we calculate the pH of a buffer system right there. We're trying to see how much of an overall change this logarithm has on the pKa, and that'll give us our overall change in pH. And I hope I laid this out pretty well. Now, this is a pretty simple form of a buffer, but what if we challenge ourselves and do a little bit more challenging of a buffer? And let's say we add some more base to the solution and throw off the whole buffer system. So we'll look at this question. When 10 millimoles of NaOH, and again, when we see OH, we're kind of knowing that when we see an OH, we're going to assume that it's a base because OH is commonly associated with bases. So I think that's actually called sodium hydroxide or something like that. Last time I took chemistry was in undergrad, so terminology could be off a little bit there, but basically when 10 millimoles of an NaOH are added to an acetate buffer, which was prepared by dissolving 20 millimoles of solid sodium acetate in 100 milliliters of a 0.4 molar acetic acid. The final pH of the solution will be blank, and he gives us the pKa of 4.7. So this problem has a lot going on. And you guys are probably like, holy cow, where do I even start? Well, let's keep it simple. Let's keep it simple, stupid. So, you guys are not stupid. You guys are academically inclined, academic weapons. You guys got this, but I'm going to keep it simple for my end because I'm not the brightest in the shed. So basically, whenever you see a question in which 10 millimoles are added, and the key word here is added, that means we already have a buffer made and we are adding additional items to that buffer to mess with the pH. I want you guys to see this right here, which I just highlighted, and save it for the very end. Cross it out of your minds, completely ignore it. What I want you guys to do is set up the original buffer solution, because he said we already have an acetate buffer and it was prepared by dissolving blank millimoles of solid sodium acetate in acetic acid. So we already know we have a buffer prepared and we're just adding another variable into it. So let's just start with the original buffer and see what we get. So we have a buffer prepared by dissolving 20 millimoles of solid sodium acetate. So we're probably sitting here like, well, is that a base or an acid? Well, if we flash down to the question right here, we can see we already have acetic acid in there, so that has to signify that this is a base. So, how I said before, I like to keep track of all my variables. So for this one, we know we have a base, we know we have an acid, we know we have a pKa, and there's just some additional conversions that we have to make. So we can see that we have a solution amount in milliliters. So let's put that variable in there. And then what else do we have? We have added. So I always like to throw down here added. So we know we add 10 millimoles of NaOH to this buffer. So we already know we have 10 millimoles of OH added. So, all right, we'll just save that for the end, but we have it down. And for our base, we know for our base, we have 20 millimoles of base. And then it shows us we have a 0.4 molar concentration of our acetic acid. We have a pKa of 4.7, and we have a milliliter amount of 100 milliliters. And what I want you guys to see is look right here for this acid. We have a molar concentration, but if we look at our base, it's in millimoles, and if we look to our added base, it's in millimoles as well. So it's going to be a lot easier to convert that acid into a millimole concentration rather than keeping it in a molar concentration. So let's do that first. And actually, just so you guys don't get mad at me for not writing the equation, I'll just write the buffer equation or the Henderson-Hasselbalch equation right here, base over acid. But for me, this is how I like to think about things, so I'm just going to go through my mindset. Step 1, find the millimole concentration of this acid right there. So we know that our conversion of a little equation from a molar concentration to millimoles is molar concentration is equal to millimoles over milliliters. And would you look at that? We have a milliliter concentration and we have a molar concentration. So 0.4 molar concentration is equal to X, which is our millimoles, over 100 milliliters. So all we do right here is times the 100 right here, times 100 on this side. So 0.4 times 100, that is going to get us 40 millimoles. So I'm going to change this little 0.4 molar concentration right here into millimoles. We have 40 millimoles. Cool. So look at that. Base, 20 millimoles. Acid, 40 millimoles. Added, 10 millimoles. And hopefully you guys don't drop the acid, but you know, that made me laugh. Okay. Don't report me to the board for that one, please. So now we have all of our variables or all of our components in the same variables. We have a pKa, we know what's added, we know what our original base concentration was, we know what our original acid concentration was. So let's fill in some variables. So we just did step 1, so step 2, fill in the variables. pH is equal to a pKa of 4.7 plus the log of base over acid. So we have 20 millimoles up top and 40 millimoles of acid on the bottom. Would you look at that? Now you're like, well, sweet, we can see how much of a pH change we had. Not yet, because we are forgetting about this added 10 millimoles of sodium hydroxide, or OH. So what I really just want to do with the equation I wrote just in step 2, I just wanted to see what we originally had in this buffer before we added anything. Because if we try to start with what was added first and don't figure out what we had originally, we're just going to be backwards. We're not going to get the right problem. So step 3 here is to add our extra base that we had. So if I were to break this down, I'm going to flash this little log system down to right here for step 3. I wrote that a little too close. We know from the problem that we add 10 millimoles of base to this buffer. So we know we have 20 millimoles of base on top, and we have 40 millimoles of base on bottom. But we added 10 millimoles of base, so base and base add together. So now after adding 10 millimoles of the additional base, we get 30 millimoles of the base. But if we add a base to an acid, the base and the acid are just going to start combining with each other, and the base is going to start taking away from the acid. So when you are adding a base to a base, you can add them together and get a higher value. But if you're adding a base to an acid, you have to subtract that amount from the acidic component. So instead of adding 10 millimoles down here, we're going to subtract 10 millimoles, which is going to give us an overall value of 30 millimoles for our acid and a new value of 30 millimoles for our base. So we just start off this little added component here, and we figured out, okay, we had our original buffer, we added 10 millimoles of a base to that, so now we have a new concentration of base and acid in this solution. So let's see how much of an influence it has on this overall system. So for step 4, we're going to find the overall difference. pH is equal to 4.7, or the pKa, plus the log of 30 millimoles of base, I'll put a big B there, and then 30 millimoles of acid. Sweet. So let's log it out. We have a log of 30 millimoles divided by 30 millimoles, or base divided by acid. And what would you know? That gives us a value of 0. Well, now you're like, well, it didn't change at all. Exactly. There will be questions on there where it doesn't change the pK or the pH at all. It does absolutely nothing. So the answer for this, the pH is just going to be equal to the pKa. So the final pH is 4.7. Or, hey, would you look at that? So many steps for absolutely nothing to happen. Oh, did I even give the answer up here? Oh, sorry, this problem was A, 4.6. But as you guys can see, there's a lot of moving components to these math questions, but I hope I laid it out really nice for you guys. And again, please text me, please give me a call, give me a ring or whatever if you guys have any issues with this. But thank you guys for listening. I know I talk quite a bit, make some really stupid, crappy jokes, but I just want you guys to be good. I want you guys to hit these problems out of the park. Hopefully when you guys get to the quizzes or exams, these styles of questions are just home runs for you guys, and you guys can just get the best scores that you guys can. So again, thank you guys for listening. Ryan Kovacic signing off.